Okay, we can represent a linear transformation, for example, this one, by a matrix quite easily. Okay, let's just say we have some matrix here, we don't know what's supposed to go into it, but it transforms xy, this, over to ax plus by, cx plus dy, this vector. What numbers or what symbols need to go into the matrix? Well, we can very quickly see that it would be AB, because then you'd have AX plus BY here, which is what you need. It'd have to be CD to give you the CX plus DY, multiply this row by this column. So that should be completely obvious at this point of the course. Okay, so that's just one example. And if you have a linear transformation, it's going to be of this form. The linear transformation from R2 to R2. So the matrix will be of this form, and there's not that much to it. Now there are other transformations, and we're going to look at a rotation transformation and a projection transformation. Okay, so take a transformation that rotates all the vectors in R3 through 53 degrees counterclockwise. Well, if this is your vector xy, then it rotates 53 degrees and ends up, let's say, here. And every vector would rotate through 53 degrees. So you can just imagine all vectors rotating through that angle. Now, in general, if you want to rotate through an angle theta, well, if this is your original vector, if you rotate it through angle theta, it ends up here. This angle, of course, will be theta greater than this angle here. And I didn't mark that angle. So the original angle with the x-axis added to whatever theta is gives you the new angle of the angle of the new vector with the axis. Now this picture got a little bit mangled, so I've drawn another one and we'll construct this. Okay, so let's say that you want to rotate this vector through angle theta. Now what I do is I say, okay, well, let's just take a tilted xy plane and call this x prime and y prime. And in this plane, this vector will then have been rotated through angle theta. In other words, the angle from here to here is going to correspond to this angle because it's equal to theta plus the angle of this vector. Okay, think through that. Okay, using this picture, we project this vector onto the x-axis, onto the y-axis, and we get an x-coordinate and a y-coordinate. We then project this x-coordinate down here, and we project this y-coordinate as well. Well, let's project the x-coordinate here onto the x-axis, and then we'll project it onto the y-axis. I say y-axis. Project it onto the x-prime axis and onto the y-prime axis. Now we're going to get a point here and a point here. So what are the coordinates, or what's the x-prime coordinate of this point, and what's its y-prime coordinate? Okay, well, the x-prime coordinate is pretty easy to see. You've got a right triangle here. It's got a hypotenuse equal to x, and the angle here is theta. So it's pretty clear that the x-prime coordinate is going to be x cosine theta. The y-prime coordinate is going to be what? It's going to be x sine theta. Now we do the same thing with the y-coordinates. So I mean, we do the same thing with this point. We find the coordinates in the prime system here. But there's the x-coordinate of this point on the y-axis, and here's the y-coordinate. Okay? The x-coordinate is going to be y times the sine of the angle from here around to here. Okay? Sine of this angle here. That angle is going to be theta, because you got theta right here, and then you got another 90 degrees. So that the x-coordinate here is y times the cosine of theta plus 90 degrees. And the y prime coordinate here is going to be y times the sine of theta plus 90 degrees. Maybe should have thought this through a little better. That's going to be the coordinate here. And that'll be right here, maybe a little bit hard to see. Well, it's going to follow that the x prime and y prime coordinates of the point xy are going to be x cosine theta plus y times the cosine of theta plus 90 degrees. So I have that down here. X prime is x cosine theta plus y cosine of theta plus 90 degrees. It's this plus this. The y coordinate, y prime coordinate, is going to be the x sine theta you get when you project here, plus the y sine of theta plus 90 degrees that you get here. Now, if we look at a triangle down here, we've got some angle theta here. Implicitly, this is theta. So here we've got the cosine of theta. Here we've got the sine of theta. Assume this is a unit vector at angle theta. Cosine theta here, sine theta here. If we rotate this vector 90 degrees, if we take the vector 90 degrees greater, we see that this coordinate becomes this coordinate, and this coordinate becomes this coordinate, but it's gone to the left. Well, if you think about this a little bit, you see that this angle from here around to here is theta plus 90 degrees. So the cosine of theta plus 90 degrees is going to be equal to the negative of the sine theta. And the sine of theta plus 90 degrees, which is this is the sine of theta plus 90 degrees, because this angle is theta plus 90 degrees, is equal to the cosine of theta. Now those are formulas that people typically memorize for about 2 hours before a test in a trigonometry class or a pre-calculus 2 class, use them and then forget about them for the rest of their lives. There's a logic behind it, there's a reason behind it, and we want to focus on the pictures and the reasons behind things rather than a bunch of formulas that we're going to forget and won't be of any use to us. Now, they can always be looked up, but you want to have a toolkit in your brain, and the toolkit should consist of being able to reason out this basic sort of stuff. Okay. Well, if we look at this expression and this expression, we see that x prime should be x cosine theta plus y cosine of theta plus 90 degrees, but the cosine of theta plus 90 degrees is the negative sine of theta. So this is don't really have room to write it, and it hasn't been written out here. I mean, this has been written. Well, you can make the jump. Okay. This is going to be x cosine theta minus y sine theta To get that for the first coordinate, you're going to have to multiply the vector xy, which represents this vector, by cosine theta negative sine theta. That row times this column gives you this. And similarly, what you get up here is going to be x sine theta plus y cosine theta, because sine of theta plus 90 degrees is equal to cosine theta. So you should get x sine theta plus y cosine theta. You do that by multiplying sine theta by the xy vector. So it all comes out of this picture. And now you've got the coordinates in a coordinate system where this, by rotating the coordinate system theta in this direction, you've effectively rotated xy by angle theta in this direction. Okay? So there you have it. This then is the rotation matrix in 2 dimensions. Okay, it's a matrix that rotates the vector xy through angle theta, and here's the result. Okay, well, rotation matrices are a big deal, and you're going to see them in your assignment. Now, what have I got next? Okay, projections. We can define a linear transformation as a projection. And really all we've got to verify to show that this is a linear transformation is if we project the vector v1 plus v2 onto w. Okay, well, the definition is transformation of any vector is its projection onto some vector w, some fixed vector w, and for the example I've chosen w equals the vector 2, 5. And now if I project v1 plus v2, then, or if I transform v1 plus v2, I ought to get the vector that's equal to the transformed v1 plus the transformed v2. That's one of the 2 conditions of linearity. Well, if I project v1 plus v2 on w, you can verify from the formula or just geometrically that that's going to equal the sum of the projection of v1 on w and the projection of v2 on w. Okay, and then projection of c times of a multiple of v. If v gets c times as long, you're going to get c times the result when you do the projection. Again, just from the geometry of the projection, but you can also do it with symbols using the formula for projection. Okay, what's that look like? Well, here's a vector. Here's an xy set of coordinate axes imposed on R2 and the vector w. And here's a vector v1. Well, we project v1 onto w, and the question came up, that dotted line makes a right angle. Well, it does. It's kind of faint, but it kind of regarded that as implicit. We want to reinforce that. Okay, so you take this vector, project it at a right angle onto w, you get this one. You project this vector onto w, well, you got to extend w along its line, but there's the projection, and well, there's the projection line, and here's the projection vector. It should be clear that any projection onto w is going to have to be along w. It's going to have to be along the line of w. So you're taking the whole space, you're taking the whole of R2, and you're collapsing it down into one-dimensional space, the space along w. So I say all vectors in R2 project to the line defined by w. Now what I mean by the line defined by w, I mean that line is defined by all the vectors in the span of the single vector w. In other words, the span of the single vector w is all the multiples of w, all the scalar multiples of w. And those scalar multiples all lie along this line, with the convention, of course, that the initial point of the vector is at the origin. If we were to project all vectors in R3 onto a plane through the origin, then again, we would be projecting onto that plane at a right angle. Okay, if this board is a plane through the origin, and I have a vector in this direction, okay, how do I project it? Well, if the origin is here and the tip of the vector is here, I bring the tip of that vector back to the blackboard at a right angle. and that'll be at a right angle with respect to any vector in the basis of this subspace. And what do I mean by that? Well, any plane is the span of two vectors. Okay, any split plane in R3 is the span of two vectors, non-parallel vectors, and non-parallel in real vector space means linearly independent. So these are two linearly independent vectors, two non-parallel vectors in the plane. Take any two vectors in this plane, take their span, and their span is going to be that plane. Okay, so, and that's this statement here. Okay, now back to the whole idea of projecting, of defining a linear transformation by projection onto this W vector. Okay, we're projecting onto the vector 2, 5. So if V equals xy, what's the projection of V onto W? Well, in general, the projection of V onto W, I like to think of it as V dotted with the unit vector in the direction of W, multiplied by a unit vector in the direction of the unit vector in the direction of W. You can think about it any way you want. You can memorize a formula, but remember what I said just a little while ago about memorizing formulas. They don't really tell you anything unless you understand what they mean. And the meaning is what I just said. Okay, well, here's the projection. Yeah, there are other ways to put meaning on it. You can do it by picture. Okay, take that picture and make sense of this formula. You can actually derive this formula from that picture. So, just to the mechanics though, we're going to project this vector on xy. We're going to use this. So, V dot W is 2 times x plus 5 times y, 2x plus 5y. Magnitude of W, well, square root of 5 squared plus 2 squared. Okay, there you have it. And then you have the vector W, which is the 2, 5 vector divided by that same square root. Well, 2 squared and 5 squared is 29. We have a square root of 29, a square root of 29. You multiply them, you get 29. So I'm just going to put the 29 under the 2x plus 5y and multiply that by the vector 2, 5, and here we have it. Okay? Now, it follows then that the vector A that represents this transformation is a vector you would multiply by xy to get this and this, and there it is. And you go back to the first example and see how that works out. If you write it out, and I didn't write this out in class, you want to say your matrix A multiplied by xy has to give you 4x over 29 plus 10y over 29 and 10x over 29, written so small even I can't read it, plus 25y over 29. And my y here looks a whole lot like an x. I probably did write it that way, so I've got to be careful. Well, what matrix do you need here? There's the matrix you need. You can easily verify it. Okay, now where's the rest of this stuff? I think I flipped the board. I've got some more stuff here. Okay, that's the board I started with. I haven't flipped it. Let me check the time here. Make sure we're not getting too long. Yeah, right at 20 minutes. So I've got time to do this. Okay. Now let's just say we use our projection matrix. Okay, so our transformation T sub proj is our transformation matrix, and there's supposed to be a colon here indicating that we're going to use this matrix to represent the projection matrix. And then we have T1, which is going to be represented by A1, and just arbitrarily I wrote 3, 4, negative 2, 7. Now, I'm getting a little superstitious about all these coincidences that have been coming up. Some of these mathematical coincidences. We've had some astounding coincidences recently in the way numbers came out. Just a minor one here is determinant of this matrix happens to be 29, but that has, I just made these numbers up. I wasn't trying to make it 29. If I'd have made this 6, the example would have been just as good, and it would have not given us a determinant that happens to be equal to this. There's no relationship between the determinant of this matrix and the determinant of this matrix, except they happen, or the denominator in this matrix, except they happen just randomly to be equal. Okay, well, enough of that. So, what do we mean then by the composition of the projection matrix with the T1 matrix? What this means is, you start with your vector space, you transform all the vectors according to this matrix. Now you don't actually do that, you wouldn't have time since there are infinitely many of them, but you imagine what the space would look like. It's going to be distorted, there might be some rotation, there might be some stretching, some compression in different directions. But that's it. Okay. And your projection matrix, well, this is the projection matrix that collapses everything onto the line of that 2, 5 vector, that W vector that we saw before. Well, if you do whatever this transformation does, and then the projection, you are going to end up with that one-dimensional subspace parallel to the vector 2, 5. So it's ultimately going to be something very much like a projection. But it's a projection of a distorted space because you're applying this transformation first. Okay, well, okay, we represent this matrix. Okay, but this is a transformation. It's a transformation that's represented by the product of the two matrices. So composition of your transformations correlates with just product of your matrices. And it's easy to understand why. If we do matrix A1 times the vector V, that transforms all the vectors according to this transformation. And then we, never mind, then we project everything onto the vector 2, 5. Okay? And that's going to be accomplished by this matrix. Well, that's really what goes on with a composition. So let's just calculate the matrix that would represent this composed transformation. So T projection dot T1 is represented by the matrix A projection times A1, and we just multiply the two matrices and we get matrix A that does this whole process without doing it just one step at a time. So using this matrix, we no longer have to multiply our V vector by A1 and then multiply that by the projection matrix. We simply multiply it. No, having trouble getting that 1 in there. There we go. Simply multiply our vector by this, and we bypass the intermediate step. Okay. Now, I want to talk just briefly about representation of a transformation relative to a basis. Okay, when you represent a transformation, this transformation, let's just take this one, T1, by this matrix, okay, that would be relative to your standard basis. Okay, your standard basis is 0, 1, 0, 0, 1. where v equals xy means x times this vector plus y times this vector. Clearly, if you do x times 1, 0, plus y times 0, 1, you're going to get the vector, you're going to get the column xy, okay? So that's representation with the standard basis, and there's not much to it. What if we wanted to represent this vector relative to the basis b equals 1, 1, negative 1, 2? What does it mean to represent this column of numbers relative to this basis? This means that the numbers xy are obtained by multiplying c1 by this basis vector plus c2 times this basis vector. Geometrically, that means we have some multiple of the vector 1, 1, which would be about there, and the vector negative 1, 2, which would be about there. Those vectors are not orthogonal. And we find the multiples that would give us the numbers xy. Okay? Now, if this is, and that representation, well, let's talk about it. Okay, for this C1 and C2, we say that xy equals C1, C2 relative to the basis B. C1, C2 relative to the basis B means C1 times the first basis vector plus C2 times the second basis vector. Just like relative to the standard basis, xy means x times your first basis vector plus y times your second basis vector. Okay, well, it looks like your vector xy, then here, if you look back here, you could represent C1 times 1, 1 plus C2 times negative 1, 2, and this should be familiar, maybe a little rusty, but should be easily recognizable. You can represent this sum by this matrix times the C1, C2 vector. So that we can find the C1, C2 vector if we know xy just by multiplying the inverse of this matrix by the xy vector. Or if we know the C1, C2, we could find xy by multiplying the matrix by the C1, C2 vector. So this matrix is the key to transitioning between representations of vectors in R2 relative to this basis and relative to this basis. So I just say, without going into more detail because we were out of time, that 1, negative 1, 1, 2, and its inverse are the transitions, represent the transitions between the standard basis and the basis B. Transitions between representation with respect to the standard basis and the basis big fancy script B. Yeah, we've seen things related to this, but this is going to be a big deal. It's going to be what we use to define the similarity transformations, and that's a huge big deal, as we'll see before too long. Okay. It's easy to construct this matrix. Okay? The matrix between your standard basis and the basis B, okay, is just obtained by putting these two vectors into columns. Now you should understand how this means this, which means the same thing as this, and understand why they go in the columns, but that's where they go. So it's kind of a mechanical process. You just put these in the columns, you find the inverse of the matrix, and now you can move from representation with respect to one basis to representation with respect to the other. And we'll follow up on that idea. That's the key idea right there.